Hello everyone, I'm Sebastian.
And I am Ed.
Welcome to the MATLAB and Simulink robotics arena. This video is an introduction to contact modeling, namely the second part of a two-video series. In the previous video, we talked about some basics of how to model contact, and then we looked at a couple of basic examples of how you would do this with Simulink. In this video, we'll continue that by talking about contact modeling with Simscape, which is our physical modeling tool. And you see that we have a couple examples of that. And then finally, we'll jump back over to the examples from the previous video. Those were a full vehicle model as well as a robot arm, and go into more details as to how that contact was implemented and maybe look at some results. That being said, let's jump to contact modeling with Simscape. So the way that normal force works in Simscape is the basic way you can do it, at least, is with these hard stop blocks. And this is a force-based penalty approach. So the way that the Simscape hard stop block works is, when you're inside of the allowable bounds of motion, then there's no force. And once you start crossing over the limits, it engages a spring and damper force. Similar to what we implemented in the previous video. On the friction side, there are also blocks for translational or rotational friction in Simscape. And these, as we discussed previously as well, they have a static and a kinetic component. The way that works is you require some initial breakaway force to move from rest to actually having some velocity. And then you also have a short transition region. Plus, once you're moving, you have a viscous friction component, which means that the force is proportional to the velocity. So these are the two kind of starter ways of modeling contact in Simscape.
I do have a question. So I see that you have two different blocks, the hard stop and also the translational friction. But what if I want to implement something that is custom to my own application, something that is different to that?
Right. So the way that these Simscape blocks work is that they always implement some kind of relationship between force and velocity. So if you have your own relationship, whether it be a lookup table or an equation, there are actually ways of grabbing the source code of Simscape blocks and then modifying them. So if anyone's interested in seeing that at a later time, let us know. Let's go into MATLAB and see some examples of this. So as a parallel to the model we showed you in the previous video, that was a Simulink penalty force contact, this is how you would model it in Simscape. So you have a mass that is, between it and the ground, we have a spring, a translational friction block, and a translational hard stop. And all the parameters are listed here. For example, the upper and lower bounds of contact, the stiffness and damping values of the equivalent spring and damper models, as well as if we go on the friction side, we have parameters such as the breakaway friction force, the viscous force, and so on. So let's look at the results here, and they should look similar to that previous model if we use the same parameters. Again, where you have an object that begins at a certain position, it bounces a couple of times against the wall, and then once it doesn't have enough energy to break away from that initial friction force, then it remains at rest for the end of the simulation.
Makes sense.
One of the things we can do with Simscape is actually log the all the quantities in the simulation. So I have a handy script-based hyperlink here, where I can plot the friction force versus the velocity that we from the simulation, and you see that this is the shape of the force versus velocity curve. So again, you see that static component at the beginning, the little transition region here, and then the viscous linear component at higher speeds. And you can do the same with rotational elements in Simscape. So this is exactly the same thing, but in the rotational domain, where you have some object with inertia that is attached to rotary springs and rotary friction. And you would see, very similar relationships when I displayed those results.
Awesome.
One of the things you notice about this is that Simscape models are one-dimensional, right? So, in the case of these models, it's been, a single mass or a single rotational object that is moving in one direction. So let's now look at some ways to, keep moving towards maybe three-dimensional contact. So the tool that we use to model three-dimensional systems is Simscape Multibody, and that's a rigid body simulation tool. moving from Simscape to Simscape Multibody, you can actually combine the functionality from the blocks that we just discussed, like the hard stop and the friction, and actually connect them to single degrees of freedom in a 3D system. Now, what that could mean, for example, is if you have a robot arm or something that has a single actuator with friction or joint limits, then this is a way to make that connection. So we'll look at how that is done, how we can interface the 3D and the 1D domains. To do that, there's actually an entry on the File Exchange online called the Simscape Multibody Multiphysics Library, which provides a couple of utilities for you to easily make this connection. So feel free to check that out. We'll look at an example of that right now.
Excellent.
Okay, so let's go over to this other section. First, I'll start with a translational example. So this is one, and actually I'll just run the simulation first. This is a block that is sliding, and it has some friction associated with it, so it comes to rest. I'll just replay that animation again. Again, it starts with some motion, and then it comes to a stop because of friction. The way that we model this is we have a solid block in Simscape Multibody that's connected to a prismatic joint, and this joint is then connected to that multiphysics library. And that causes the bridge between the 3D model and the translational friction. And just as before, we can grab the logs and plot our friction force versus velocity. So in this case, this is showing it just in one direction because our log data starts at 0 speed and then moves up to a final velocity. Yeah.
So if you go to that scope in the velocity plot, I see that there's a little jump when the body is coming to rest at about 3.5 seconds. Can you explain what that is right there?
Yeah, let's zoom in. So this has to do with the nonlinear relationship of the friction, right? So basically what happens is that this object is slowly decelerating, but as it engages that kind of limit region where all of a sudden you don't have enough to keep moving, then you get into the static region where the object just immediately stops moving. So this is the transition here between static and kinetic friction.
Sense.
So this example, it doesn't have much of a 3D element to it. We can start looking at other types of things. For example, if we use the same kind of interface for a rotational element where we're going to use a hard stop in this case to enforce limits on a rotational or revolute joint in Simscape Multibody. You see that you have this pendulum that falls down and then it bounces against its limits and finally comes to rest. And again, we can see here, we can plot our friction torque versus the velocity, and we should get that similar shape as before. But in addition, you have hard stop forces coming into play at each of these bounces in the simulation. So that's a start. Like I said, this kind of approach, and let me actually go over to the multiphysics library. This approach is good if you're trying to just add some dynamics to individual actuators or joints in a full 3D model. You see here you have things like the translational or rotational interfaces, as well as some other utilities to help you do this with more elaborate connections, maybe like hydraulic cylinders or electromechanical connections. So check this out.
So you just mentioned that this is a good method for doing it in single actuators and single joints, but what if I don't want to constrain my model to just that? What other options do I have?
So there is also a second library available on File Exchange called the Simscape Multibody Contact Forces library. And this contains a couple of blocks to let you model contact between simple shapes like spheres or planes, in full three-dimensional contact with each other. So if you need to model something like that, where it's not just along one direction of motion, but actually a full contact formulation, then I would recommend starting with this library. So the way this works, for example, if you have two bodies, you go into this library and you have a block that does all this. For example, a sphere to plane force. So if you're able to make your problem also be the same kind of thing, where you have simple shapes in contact with each other, you can certainly use this library. So we'll start with a model of a sphere coming into contact with a rigid plane using the contact forces library. As you see here, we have basically a plane that's fixed to the world, a sphere that is able to freely move with a 6-degree of freedom joint. And in between, we just have that sphere to plane force. So I'll go ahead and simulate that. Here you'll see again there's a sphere that's bouncing, and then it falls off the plane. If I go back and actually select the sphere itself and replay it, you'll see that the sphere actually falls, and because of friction force, it also starts to spin as it rolls off the plane. And the reason it does is because the plane is actually angled in this case. Otherwise, it would just stay in the middle.
Sebastian, I know we also covered an example when the plane might not be fixed. What happens when that is the case? Can I model that with multibody as well?
Yeah, absolutely. So in this case, the only reason this plane is fixed is because, like I said, this is rigidly connected to the world. The way that these blocks work is that they will apply the forces to both sides of the contact. So if I open up the version that does have a moving plane, in this case I've also added a 6-degree of freedom joint, between the plane and the world, and I maybe change a couple of the parameters of motion. But then if I run this, you'll see that the plane, let me actually go back and slow it down to half speed. You'll see that now the plane is free to move, right? So as the ball falls down to the plane, it actually dips down because of the weight of the ball. And then as the ball starts sliding off, the plane's actually rotating because, once you get off the center of mass of the plane, it causes a torque, and then the ball is gone again. And the only change that was done from a user point is that I added this degree of motion. This block, like I said, takes care of all of that. And this is the way that it works, just to kind of summarize that. Let's say you have two objects, and everything in blue there is a schematic of what's inside the contact forces library block. The first thing you need to do is take advantage of the transform sensor block in Simscape Multibody. That gives you basically things like positions and velocities between two bodies. So you have to measure things between the sphere and the plane, let's say. Then comes the fun part, which is to actually calculate the contact force and torques. So you take all the quantities that you measured, figure out whether there is contact, what the normal force is, what the friction force is, all in 3 dimensions. So this is the part that involves math, and why we'd recommend trying the library first. However, if you find that you need customizations, you can always take a look at these blocks and implement your own relationship. Then there are blocks called external force and torque. So what you then do is, once you've computed the forces on both sides of the contact, then you apply them to the respective coordinate frames, so on both the base and the follower side of the contact.
Makes sense. So these are the blocks kind of taking care of the reaction forces that you experience, right?
Right. And the last thing to note is that these forces require the bodies to be free to move in some way. Like in this case, if the two bodies are completely free, then there's going to be 2 independent 6-degree of freedom joints between each side of the contact and the world. And what holds them together is that contact force.
Makes sense.
So now that we know a little bit about different approaches of modeling contact with Simscape, let's actually go back to the examples that we showed in the first video and see how they work. So let's start with the car model. Let's open this up over here. And again, this is the same model from the previous video. If I go to the animation here, as you recall, when I run this, what's happening is the car is moving forward some speed, and then it turns. So tell us more about what's going on under the hood.
Right, so you saw that the steering input is given at about 3 seconds. So what we're interested in is the contact characteristics and how this changes. Yeah, 3 seconds the steering input. So what about the contact in terms of the normal forces and also the friction forces? We can see the difference between the right wheels and the left wheels because there's some displacement that happens with the weight as we turn, right? So if we go to the Simulink data inspector, we already have our data loaded here, but you can see that for the front, for the left wheel, the normal force is higher because we're turning right, so with that weight shift, the left wheel would have a little bit more of normal force, right, in the up direction. And that's what you can see there in that divergence after about 3 seconds. So based on that, we can also analyze the friction force, and that's the bottom subplot. And what you can see is with the increase in normal force, you also have higher friction. And we remember that the friction is a function of the normal, but also of speed. And since we're turning right, the left wheel has a higher speed, and therefore we get a higher friction force, as shown in the blue line there at the bottom.
Let's go back into the model and take a look at where all this data came from. So let's go into maybe is it the front right wheel?
Yep.
So if we look in here, I guess, here we go.
So what we're using here is the contact forces library that we discussed. And here what I'm using is the interface between a sphere and a plane, right? So here I define the parameters for the sphere, its radius, and also some parameters for the plane, and also the parameters for my contact and the friction forces.
Again, I see that these blocks actually come with output measurement buses, as we saw before. So we're just grabbing the normal and the friction forces and then logging them to the
Exactly.
data.
Exactly.
Awesome. So let's see how the robot arm model was implemented and kind of take a look at some of these things in a similar way. So if I open this up, for this one I'll actually go through the model first. If I start digging in through the robot model, eventually I'll get to this environment section. And as you recall, there are actually two different types of contact in this model. First of all, there's a gripper force. So in this case, if I start digging into the gripper force, you'll see that this is modeled using one of the composite plane-to-face force blocks. If I double-click this block, you see that it's basically just 4 points that are in contact with the plane. So that's where the gripper comes into contact with the face of the box. And same thing with all the parameters that have been chosen for this. And then for the conveyor belt, if I go up to the conveyor subsystem, then here we have contact for basically the two different belts, the input and the output belt. And this one we're using a box-to-belt force. Just to recap, a lot of these blocks would come from the contact forces library that you can get on the file exchange, like the face-to-plane and the face-to-belt that we've shown. So if we run this model, just as a reminder, restart this, you'll see that it starts with the box in contact with the conveyor belt, then it leaves the first belt, it's grabbed by the robot, and then it's put down on the second conveyor belt. So let's take a look at some of the contact forces that went into play there, also by looking at the data in the simulation data inspector. Looking at our log data here, this is my latest run. At the bottom here, I'm actually going to plot two signals that I have called belt_in.box and belt_out.box. These signals basically just tell you whether the belt is detecting that the box is on it. So you see between about half a second and 6 seconds, then there's a box in the first belt. And then from 10 seconds onwards, there's a box on the second belt. And in between, of course, is when the gripper actually picks up the object.
Yeah.
So if we go look at the contact forces from this logged run, if we look first of all at the normal force of the input belt, you'll see a very sharp spike at the beginning because, I don't know if you saw it, but the box actually started in the sky and it fell on the conveyor belt. So let's zoom in here. And again, you'll see what's going on with the normal forces. Again, while the box is on the belt, you actually have a normal force. And then these other spikes that you see here have to do with change in normal force when you start moving and stop moving the conveyor belt. And then similarly for the belt out normal force, if we were to plot that, and once again rescale to avoid the spikes, you'd see that basically these forces mimic what's going on here. And of course in the middle here we can plot some of the normal forces of the gripper fingers. So here for example we have, and once again we'll rescale, the normal force on the gripper, and you see that this normal force is bigger than the one on the belt because you actually have to basically squeeze even harder on that box to be able to lift it up and drag it around on the ground.
I see.
And that happens basically right in between those other two normal forces. So now let's get back to some key takeaways. As we saw in Simulink, you can model both impulse-based and penalty force contact. However, all the equations of motion of the mechanical systems need to be derived and implemented. On the Simscape side, we saw that because of the force versus velocity relationship in the blocks, that the approach to do this with Simscape is with a force-based contact only. However, you get the advantage of being able to easily create physical models without building equations, whether it be a one-dimensional or a three-dimensional system. Then we have all these utilities available that to give you a starting point for contact, like the one-dimensional hard stop and friction blocks, and things like the contact forces library that you can find on File Exchange. So thank you for watching this video. As always, feel free to contact us via email or Facebook, and check out the other resources below. Thank you.
Bye-bye.